Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore AWS Batch, a powerful service that enables you to efficiently run hundreds to thousands of batch computing jobs on AWS. Whether you're processing large datasets, performing scientific simulations, or running ML model training at scale, AWS Batch removes the heavy lifting of provisioning and managing compute infrastructure. We'll walk through the core concepts, architecture, key components of AWS Batch, and share best practices for scaling workloads, optimizing costs, and integrating with containerized environments. Let's get started. Before we dive into AWS Batch, let's first understand what batch computing is and why it's so critical in today's data-driven landscape. Batch computing is a method of executing a series of tasks or jobs without manual intervention. These jobs are often grouped and processed in bulk. Think large-scale simulations, data transformations, or media rendering, typically running to completion based on predefined schedules or triggers. It's a fundamental paradigm in fields like life sciences, engineering, financial services, and machine learning, where workloads can be parallelized and don't need real-time interaction. For example, you might need to process thousands of video files overnight or train multiple ML models in parallel across different hyperparameter sets. Traditionally, managing batch workloads meant setting up complex infrastructure, clusters of machines, job schedulers like Slurm or Grid Engine, dependency management, error handling, and fine-tuned scaling. These environments were not only hard to maintain, but often led to underutilized compute resources and inefficient operations. Cloud-based solutions like AWS Batch completely reimagine this model. Instead of managing servers and queues yourself, AWS Batch handles compute provisioning, scaling, and job orchestration for you, on demand. You submit a job, define your requirements, and Batch spins up exactly what you need, whether it's a single container or thousands running in parallel. AWS Batch is a fully managed service that makes it easy to run large-scale, parallel, or high-throughput batch computing workloads in the cloud, without having to manage your own infrastructure. At its core, AWS Batch dynamically provisions compute resources based on the specific needs of each job you submit. Whether your job requires a single vCPU or hundreds of GPU cores, AWS Batch automatically scales the right resources up or down, helping you optimize both performance and cost. What makes AWS Batch especially powerful is its seamless integration with container technologies. You package your workload into a Docker image, store it in Amazon ECR or Docker Hub, and Batch takes care of launching and running your job in a containerized environment using Amazon ECS or AWS Fargate. You don't need to worry about spinning up or managing clusters. AWS Batch provisions compute environments as needed, runs your jobs, and tears everything down when it's no longer required, making it cost-effective and operationally simple. It supports job queues, prioritization, and even job dependencies, so you can build complex workflows where one job starts only after another finishes. With array jobs, you can efficiently run thousands of similar jobs in parallel, like splitting a dataset for parallel processing or sweeping across hyperparameters. Batch also gives you fine-grained control over the compute environment. You can choose specific EC2 instance types, mix on-demand and spot instances for cost savings, or use Fargate for serverless execution. And finally, AWS Batch integrates seamlessly with services like S3 for data, CloudWatch for logging and monitoring, IAM for access control, and step functions for orchestration, making it a powerful building block for modern, scalable batch pipelines. To effectively work with AWS Batch, it's important to understand its core components, the building blocks that define how jobs are created, scheduled, and executed. First, at the heart of everything is the job. A job represents a unit of work, for example, running a script, training a model, or processing a dataset. Each job specifies the container image to use, the compute requirements, environment variables, and any parameters it needs at runtime. Next is the job definition, which acts like a blueprint for how jobs should run. It includes key configuration details like the Docker image, vCPU and memory settings, IAM role for execution, retry strategies, and timeouts. Once defined, you can reuse job definitions across multiple job submissions. Job queues are the staging areas where jobs wait to be scheduled. Each queue can be mapped to one or more compute environments, and AWS Batch uses job priority to decide the order of execution when resources become available. Compute environments, or CE, provide the actual infrastructure to run jobs. These can be managed, where AWS handles provisioning EC2 or Fargate resources, or unmanaged, where you supply your own. You can configure CEs with a mix of on-demand and spot instances to balance performance and cost. The scheduler plays a central role by continuously monitoring queues and dispatching jobs based on priority, resource availability, and job requirements. It ensures efficient and fair resource utilization. AWS Batch also supports array jobs, which allow you to run thousands of similar jobs in parallel, ideal for tasks like data chunking, Monte Carlo simulations, or hyperparameter tuning. And finally, with job dependencies, you can define workflows where jobs only run after other jobs succeed, enabling complex multi-stage pipelines directly within AWS Batch. Let's take a closer look at how AWS Batch orchestrates the lifecycle of a job through two interconnected layers: the system architecture and the job flow. On the left side of the diagram, we see the division between the AWS managed infrastructure and the customer's AWS account. Within the AWS account, AWS Batch acts as the central orchestrator. The job scheduler is responsible for managing job submission, determining execution order, and matching jobs to available resources. Beside it, a compute scaler dynamically evaluates job demand and works with the customer's account to provision the appropriate compute capacity. That capacity is fulfilled in the customer account, where an auto-scaling group manages the life cycle of both on-demand and spot instances. This dual-mode compute strategy ensures cost efficiency while maintaining performance and reliability. Alongside compute, the storage layer, featuring services like Amazon EBS for ephemeral storage and S3 for persistent data, is depicted as part of the customer's infrastructure, supporting input, output, and checkpoint data for jobs in flight. On the right side, we walk through the job lifecycle itself. It all begins with a job definition. This serves as a blueprint, specifying everything a job needs, including the container image that defines the runtime environment. From this definition, a job is created, and while defaults are applied, some parameters, like input data or command overrides, can be customized at submission time. The job is then sent to a job queue, which organizes and prioritizes jobs based on their assigned compute environments. Each compute environment represents a collection of EC2 or Fargate resources available for executing jobs. These environments can be linked to multiple queues, providing flexibility and redundancy. Once scheduled, the job is launched into its compute environment, where the specified container image is pulled and executed. AWS Batch continues to monitor the job's status, handling retries, logging, and teardown automatically upon completion. This dual-layer model, separating orchestration from execution, enables AWS Batch to scale batch workloads seamlessly, automate resource provisioning, and reduce operational overhead, making it a powerful tool for running compute-heavy workloads in the cloud. In AWS Batch, the job definition is the blueprint that tells AWS how to run a job. It's one of the most critical components because it encapsulates everything the service needs to know about your workload. At the core of the job definition is the container image. This image contains the application code, scripts, libraries, and any dependencies your job needs to execute. It can be pulled from Amazon ECR, Docker Hub, or any supported container registry. You also specify the compute resources required for the job, things like the number of vCPUs, the amount of memory, and optionally GPU requirements. This helps AWS Batch provision the appropriate infrastructure for your workload. Job definitions also support environment configuration. You can pass in environment variables, secrets, and command line arguments to parameterize your job at runtime, making it reusable and flexible. This is especially useful for running the same container with different datasets or parameters. The IAM role associated with the job definition grants your job permissions to access other AWS services. For example, your job might need to pull data from S3, write logs to CloudWatch, or query a DynamoDB table. All of that access is managed securely through the execution role. You can define retry strategies to control what happens if a job fails. AWS Batch can automatically retry the job a specified number of times, helping increase reliability. Timeout settings ensure that jobs don't run indefinitely in the event of a hang or error. Job definitions also support array properties and dependencies, allowing you to run many similar jobs in parallel or build sequential workflows where one job starts only after another completes. Finally, AWS Batch supports versioning of job definitions. You can create multiple revisions, test new versions safely, and roll back if needed, giving you control over your production workloads as they evolve. AWS Batch uses a powerful and flexible scheduling and queuing system to manage the flow of jobs from submission to execution. When you submit a job in AWS Batch, it's placed into a job queue, a logical staging area where jobs wait until compute resources are available. These queues are decoupled from the compute environments, giving you the flexibility to associate multiple compute environments with one or more queues. Each queue is assigned a priority, which determines how jobs are serviced when multiple queues share the same compute environment. Higher priority queues will be scheduled first, enabling you to control which workloads take precedence in a multi-tenant or multi-stage pipeline. Within each queue, jobs are typically processed in a first-in, first-out fashion. However, if a job has dependencies, for example, it must wait for another job to complete, the scheduler will honor those conditions before executing the job. You can define job dependencies, allowing you to chain jobs together in a workflow, where one job runs only after one or more parent jobs finish successfully. This is extremely useful for building multi-step pipelines like data preprocessing, model training, and evaluation. AWS Batch supports automatic retries based on your job definition's retry strategy and handles failure gracefully, helping to keep your pipelines resilient without manual oversight. Finally, the AWS Batch Scheduler continuously evaluates job queues and available compute resources, dynamically assigning jobs based on current demand, instance capacity, and execution constraints. This ensures jobs are executed as efficiently and cost-effectively as possible. To understand how AWS Batch manages the lifecycle of a job, it's essential to look at the various states a job moves through, from submission to completion. The lifecycle begins with the submitted state. At this point, the job has been accepted by AWS Batch and placed into a job queue. It's essentially in line, waiting to be evaluated by the scheduler. Think of this as the starting point in the journey. From there, a job may move into the pending state. This happens when the job has unmet dependencies, such as another job it's waiting for to complete, or when it's part of an array job or a job dependency chain. Pending jobs are temporarily blocked until those prerequisites are resolved. Once all dependencies are cleared, the job transitions into the runnable state. This is where the AWS Batch Scheduler actively evaluates the job against available compute environments, resource availability, priorities, and fair share settings. It's ready to run, but waiting for the right time and place. Next is the starting state. This indicates that the job has been assigned to a compute environment and the container image is being pulled. The EC2 or Fargate instance is warming up and the job is being initialized. It's not quite executing yet, but it's getting close. When execution begins, the job enters the running state. At this point, the container is live, your command is executing, and AWS Batch is monitoring logs, metrics, and health in real time. This is where the bulk of the workload is performed. After execution, the job will reach one of two terminal states, succeeded or failed. A succeeded state means the job completed normally, returning an exit code of 0. This typically indicates that the workload ran as expected. On the other hand, a failed state means the job exited with a non-zero code, which could point to runtime errors, container issues, or misconfiguration. In AWS Batch, compute environments are the execution layer where your batch jobs actually run. Think of them as the infrastructure pools that AWS Batch uses to launch resources based on your workload's needs. There are two main types of compute backends you can choose from: EC2 and Fargate. EC2 offers deep control over instance types and configurations, perfect when you need specific hardware. Fargate, on the other hand, provides a serverless compute model where AWS abstracts away infrastructure management entirely, letting you focus purely on your code and resource requirements. AWS Batch supports both managed and unmanaged compute environments. In a managed environment, AWS takes care of provisioning and scaling EC2 instances based on your job demand. With unmanaged environments, you can bring your own EC2 instances and register them manually, giving you full control over patching, software, and system settings. You can define minimum, desired, and maximum vCPUs for each compute environment. AWS Batch uses these thresholds to scale resources dynamically as jobs enter and leave the queue. This elasticity means you only pay for the resources you actually use. To optimize cost, compute environments can be configured to use on-demand instances, spot instances, or a mixed strategy. Spot is ideal for fault-tolerant workloads that can handle interruptions, offering substantial cost savings. You also have the flexibility to define allowed EC2 instance types and use custom AMIs, which is useful for workloads requiring specialized drivers or pre-installed software. A single job queue can be mapped to multiple compute environments, which gives AWS Batch the ability to choose the most optimal resource pool based on availability, pricing, and job requirements, helping you balance performance, cost, and reliability. Finally, resiliency and fault tolerance for batch-managed compute environments is achieved by automatically replacing unhealthy instances and retrying failed launches. This ensures high availability and workload continuity. Containerization plays a central role in how AWS Batch runs and scales workloads. It brings consistency, portability, and efficiency, all of which are critical for modern batch processing pipelines. At its core, a container bundles your application code, libraries, dependencies, and runtime environment into a single portable image. This guarantees that your job behaves the same way, whether it's running on your laptop, in a test environment, or on AWS Batch. Eliminating the "it works on my machine" problem. One of the major benefits of using containers is isolation. Each job runs inside its own container, securely sandboxed from other jobs and the host infrastructure. This not only enhances security, but also prevents one job from interfering with another. AWS Batch supports container images from Amazon Elastic Container Registry, ECR, Docker Hub, or other public registries. This gives you the flexibility to pull pre-built images or build and store your own custom containers optimized for your specific workloads. Containers are also lightweight and fast to launch, which means reduced startup latency, especially important for high-throughput environments where thousands of short-lived jobs may run per day. You get granular control over resources. With each job, you can specify the exact CPU and memory requirements, ensuring efficient resource utilization and minimizing cost from over-provisioning. Finally, containers also support parameter injection. You can pass environment variables, command line arguments, or secrets into your container at runtime, enabling flexible, reusable job definitions. All of this makes containers the perfect fit for batch workloads, combining flexibility, scalability, and control in a way that traditional compute models struggle to match. Security and compliance are foundational elements of any compute platform, and AWS Batch is designed with both in mind. It integrates natively with core AWS security services to ensure your workloads are protected and compliant with enterprise-grade standards. First, AWS Batch leverages IAM roles to enforce fine-grained access control. You can assign IAM roles to jobs, compute environments, and the batch service itself, ensuring that each component operates with the minimum required permissions, a key tenet of the principle of least privilege. For network security, jobs run within your Amazon VPC, allowing full control over subnet configurations, security groups, route tables, and NAT gateways. This enables true network isolation, which is especially important in multi-tenant or sensitive environments. Data security is addressed through encryption at rest and in transit. AWS Batch supports AWS KMS to encrypt data on storage volumes and uses TLS to protect communication between services, job containers, and other AWS resources. When using container images, you can pull from private Amazon ECR repositories, ensuring that only authorized users and systems have access. You can even restrict ECR access to specific VPC endpoints for maximum control. Secrets and credentials are managed securely using AWS Secrets Manager or Systems Manager Parameter Store, allowing jobs to access sensitive data at runtime without hard-coding values into your containers. From a monitoring and compliance standpoint, AWS Batch integrates with CloudTrail, CloudWatch, and AWS Config, giving you deep visibility into job activity, infrastructure events, and configuration changes. This helps meet audit requirements and supports incident response. Finally, each job in AWS Batch runs inside a separate container with resource limits you define, providing strong isolation and preventing resource contention or privilege escalation. When it comes to AWS Batch, one of the most appealing aspects is its pricing model. It's simple, transparent, and aligned with the underlying compute resources you use. AWS Batch itself comes at no additional cost. That means you're not paying for the batch orchestration layer. You only pay for the compute and storage services your jobs consume. The core driver of cost in AWS Batch is the compute environment. If you're using Amazon EC2, charges are based on the instance type, size, and duration of usage. You can choose between on-demand instances, where you pay for compute capacity by the hour or second with no long-term commitment, and spot instances, which offer steep discounts by using spare AWS capacity. Spot pricing can reduce your compute costs by up to 90%, though these instances can be reclaimed by AWS with short notice, making them ideal for fault-tolerant or stateless batch jobs. If you're using AWS Fargate, pricing is based on the vCPU and memory requested for each job, billed per second with a 1-minute minimum. This serverless compute model eliminates the need to manage EC2 instances entirely and is great for customers who prioritize operational simplicity and elasticity. Storage and data access can also influence your total cost. Jobs that use Amazon EBS volumes will incur additional storage charges, and accessing large datasets from Amazon S3 or transferring data across AWS regions or outside of AWS can lead to data transfer costs. Additionally, while data transfer within the same availability zone is generally free, cross-zone and public internet traffic may come with associated charges. Planning your data flow and compute placement can help manage these networking costs effectively. So while AWS Batch itself is free, your job architecture, including compute strategy, storage, and data movement, will determine your final bill. A smart design can go a long way in keeping costs predictable and optimized. Cost optimization is a critical part of any successful AWS Batch strategy. With the right architectural choices, you can significantly reduce expenses while still meeting performance and scalability goals. First, one of the most impactful cost-saving techniques is to leverage EC2 spot instances. These instances allow you to tap into unused AWS capacity at a fraction of the on-demand price, sometimes offering up to 90% in savings. They're ideal for stateless, fault-tolerant, or parallelizable batch workloads that can tolerate occasional interruption. For short-lived or lightweight tasks, AWS Fargate can be more economical. It removes the need to manage EC2 capacity, billing you only for the exact CPU and memory used per second. This is especially valuable when you have highly variable or bursty workloads with low operational overhead. Another important practice is to right-size your jobs. By specifying the minimal vCPU and memory needed in your job definitions, you avoid over-allocating resources, which translates directly into cost savings. To increase scheduling flexibility and reduce queue backlogs, consider configuring your compute environments to support multiple instance types and architectures, including ARM-based Graviton processors. These provide excellent performance at a lower price point. Consolidation can also help. If you have many small, fast jobs, grouping them into a single containerized batch task can reduce startup time and resource overhead, leading to better overall efficiency. It's also essential to optimize your use of storage. Use ephemeral storage where possible, clean up unused EBS volumes, and minimize cross-region data transfers. Even small adjustments here can have a significant impact on monthly costs. Lastly, use AWS Budgets, Cost Explorer, and CloudWatch to monitor your job spend in real time. Set alerts and thresholds to catch runaway jobs or misconfigured environments before they impact your bottom line. Effective monitoring and observability are essential for running reliable and cost-efficient batch workloads. AWS Batch provides deep integration with AWS native tools, giving you robust visibility into both job execution and infrastructure health. Let's start with Amazon CloudWatch logs. Each batch job streams its standard output and error directly to CloudWatch, enabling you to view logs in real time or review them later for troubleshooting and performance analysis. This is especially useful when trying to understand why a job failed or behaved unexpectedly. On the metrics side, CloudWatch Metrics provides detailed insights into your batch environment. You can monitor job queue depth, job states, and the provisioning and utilization of compute resources. These metrics help you detect bottlenecks, such as jobs stuck in the runnable state, and make data-driven scaling decisions. AWS Batch also gives you detailed job lifecycle visibility via the console, CLI, or API. You can track a job's journey from submitted to completed, including all intermediate states like runnable, starting, and running. This transparency is crucial for monitoring SLAs and understanding workflow timing. For security and compliance, AWS CloudTrail captures all API activity, including job submissions, job status changes, and compute environment updates. This helps with auditing and root cause analysis. Custom CloudWatch alarms and dashboards can be created to alert teams when thresholds are breached, such as too many failed jobs or high CPU usage. And if you're looking for deeper container-level insights, enabling ECS or Fargate Container Insights gives you visibility into per-container CPU, memory, and I/O metrics. Finally, AWS Batch works well with third-party observability platforms like Datadog, Prometheus, and Grafana, allowing you to correlate batch metrics with the rest of your infrastructure in a unified monitoring plane. When evaluating batch processing frameworks, it's important to understand how different tools are built for different needs. Let's compare three widely used systems: AWS Batch, Apache Airflow, and Slurm, each designed with a unique philosophy and set of trade-offs. Starting with purpose, AWS Batch is purpose-built for running large-scale batch computing workloads in the cloud. It's deeply integrated with the AWS ecosystem and designed to abstract away infrastructure management. In contrast, Apache Airflow is a workflow orchestration tool for data pipelines or machine learning workflows. Slurm, on the other hand, is a high-performance computing scheduler built for running parallel or tightly coupled scientific applications on shared compute clusters. On the compute management front, AWS Batch is fully managed. Airflow doesn't manage compute directly. Instead, it schedules tasks on whatever infrastructure you connect it to, unless you are using MWAA. Slurm requires manual provisioning and configuration of compute clusters, often on-premise or in fixed cloud environments. AWS Batch is ideal for stateless containerized workloads. Airflow supports a wide variety of tasks, but it's best for orchestrating workflows rather than running compute-intensive jobs. Slurm excels in running tightly coupled parallel jobs, often written in MPI or OpenMP, making it ideal for scientific research and simulations. AWS Batch automatically scales based on job queue depth and compute environment configuration. Airflow's scalability is tied to the underlying infrastructure and executor type. Slurm's scalability depends on the size of the provisioned cluster and can handle thousands of nodes, though it lacks cloud-native elasticity. Lastly, on pricing, AWS Batch is a managed service, so you pay only for the underlying compute resources. There's no charge for the service itself. Airflow is open source, but your costs depend on the compute platform you tie it into. Slurm is also open source, but it requires investment in infrastructure and skilled admins to maintain. In summary, AWS Batch is best when you want scalable, hands-off batch computing in the cloud. Airflow shines in orchestrating multi-step workflows across systems, and Slurm remains the go-to for high-performance scientific workloads on shared compute infrastructure. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.